In this video tutorial, we will review periodic trends and chemical bonding. So much of this should be a review from grade 11 chemistry. So let's begin with atomic radius. That essentially describes the average size of an atom. If you recall, the Heisenberg uncertainty principle states that we can never know where the electron exactly will be at any given point in time. As such, we can only tell where the electron will most likely be. And so we can only use average sizes, not exact sizes for the atom. Now, the size of the atom increases as you go from top to bottom because the number of shells, or electron shells rather, increases as you go from top to bottom on the periodic table. Now, a common misconception students have is that they believe atoms get bigger and bigger as you go from left to right because it increases the number of protons, so obviously the atom must get bigger. That is incorrect. In actuality, increasing the number of protons actually makes it smaller and smaller. This is due to something called effective nuclear charge. The symbol we use is ZF. Let's compare these two electrons here. They're both in the second shell, and they're both attracted to the nucleus. However, they both have two electrons that block the view of the nucleus. So here we go, two electrons that block the view of the nucleus. This is known as electron shielding. So the electrons shield the nucleus, preventing it from attracting the electron as much as it could have without the electron shielding. And that of course affects the effective nuclear charge, meaning how well the nucleus can attract the electrons. Now what about these electrons over here? Do they not participate in electron shielding? Yes, they do, but they won't have as much of a shielding effect as electrons in the core shells. Obviously, this is a simplified diagram of the atom, so my explanation is not perfect, but you will notice that these electrons are on the same energy level as the electron that we're talking about over here. Because they're on the same level, it won't block the view of the nucleus as much as the core electrons. So again, comparing these two electrons, they are on the same shell, second shell. They have two electrons, primarily, that will block its view. So everything's identical, everything's fair between the two. The only difference is the number of protons in the nucleus of each atom. Since lithium has 3 protons, while fluorine has 9 protons, that means that fluorine is able to greatly attract the electron towards its nucleus more than lithium can. Due to the greater attraction, fluorine can hold the electron closer to its nucleus than lithium can. Thus, fluorine's atomic radius is slightly smaller than lithium's. And so the overall trend for atomic radius is to go in this direction, where the smallest atom on the periodic table is up in the top right-hand corner, and the largest atom on the periodic table is in the bottom left-hand corner. Now, if you wanted to compare between these two atoms over here, the one that has more shells is definitely going to be the larger one. But if they were side by side, the one furthest to the left would be the one that's larger because it has fewer protons to attract electrons. So the next trend we'll be looking at is called ionization energy. This is the amount of energy required to remove the outermost valence electron from an atom. Greater electron shielding decreases the amount of ionization energy needed to remove a valence electron. With greater electron shielding, it becomes more difficult for the nucleus to hold on to the electron. And so the further away the electron is, the easier it is to rip off the electron, the less energy required to rip off that electron, lower IE. Versus if you have very little electron shielding, the nucleus can now hold on to the electron very, very tightly, and then you're going to spend a lot more energy to try to rip that electron off, so you have an increased ionization energy. Thus, as the atomic radius increases, the ionization energy decreases. Now, first ionization energy is the energy required to remove the first valence electron, while second IE is energy required to remove the second valence electron, and so on and so forth. And so the more electrons you remove, the more difficult it is to remove subsequent electrons. So the third ionization energy is generally larger than the second, and this is generally larger than the first. The next trend we'll be looking at is called electron affinity, EA. Electron affinity is the change in energy when an electron is added to an atom. So while ionization energy is the change in energy when you remove an electron, EA is the change in energy when you add the electron instead. Now take a look at lithium. With lithium, you can either gain 7 electrons to achieve a full valence shell and become stable, or you could lose 1 electron so you could have a full valence shell. Obviously, it is much easier for metals to lose 1 valence electron than it is to gain 7. With a non-metal like fluorine, however, it is much easier to gain 1 electron than to lose 7 electrons to achieve the full valence shell. So by adding 1 electron to fluorine, you have made it very, very stable. And if you recall, high energy typically means low stability, while low energy typically means high stability. And of course, energy can't be created or destroyed. So when we add this electron to fluorine, we make it very, very, very stable. In the process, it goes from a high energy state to a low energy state, or we say it's ground state. But of course, energy cannot be created or destroyed, and so the energy lost, or released rather, in this process is known as electron affinity. It gets a negative value because we're releasing the energy. So the energy is being lost by the atom and given off to the surrounding area, and that's why EA is a negative value. Looking at lithium, however, gaining an electron doesn't really help the lithium become super stable. Remember, it would have to gain 7 more electrons to achieve a full valence shell. So adding 1 extra electron doesn't really help lithium all that much. That is why its EA value is much smaller than fluorine's. By adding electron to lithium doesn't really do too much in terms of stability, so very little EA is released, but adding electron to fluorine does a lot for its stability, so a lot of energy is released. But what if you try to add an electron to something that's already stable? Helium, for instance. So helium is already quite stable. By adding an electron in, you destabilize it. As we saw over here, if you have low stability, you have high energy. So in the process, you're giving energy to the helium to make it unstable, and that's why its EA value is going to be positive. And so typically, noble gases, their EA values will be a positive value because adding an electron to it makes it unstable, and in the process, adds energy to the atom. Now, it's much easier to add an electron to a smaller atom than it is trying to add an electron to a larger atom. Larger atoms, the nucleus is so far away with so much electron shielding, it's hard for that electron to get locked in. Whereas with a smaller atom, because the nucleus is so close to where the electron is, it's much easier for the electron to be attracted to its nucleus. As such, electron affinity generally increases from left to right and bottom to top, all right? Where the smallest atoms are the ones with the highest EA, and the largest atoms are the ones with the lowest EA values, which is the same pattern for ionization energy as well. Now, the last trend we want to look at is called electronegativity, EN. This is the relative measure of an atom's ability to attract shared electrons in a chemical bond. So how well can an atom attract electrons towards its nucleus? This is a scale from 0 to 4, where 0 has low attraction and 4 means high attraction. Just like the last two trends, the smaller the atom, the greater the attraction for electrons, while the bigger the atom, the farther away and the less the attraction for electrons. As such, greater electron shielding decreases an atom's EN value, while an atomic radius increase results in electronegativity decrease. Alright, so for our next topic, let's go over the different models of chemical bonding. In grade 10, you probably would have learned about the ionic bond and the covalent bond. In grade 11, we introduced the nonpolar covalent and the polar covalent bond. And this year, we're going to introduce the metallic bond. So, why chemical bonds? If you recall, noble gases are the most stable elements on the periodic table. What do they all have in common? A full valence shell. As such, an atom tends to gain or lose electrons to become isoelectronic with the noble gas it is closest to. So isoelectronic means the same electron configuration, so the same electron pattern as the noble gas it is closest to. Take a look at fluorine. When fluorine gains an electron, it now has 8 valence electrons, and it is isoelectronic with neon, which also has 8 valence electrons. Now, how an atom gains or loses electrons determines the type of chemical bond that is going to be formed. This in turn imparts the substance with special physical properties. Now, throughout the unit, I will be using the phrase form follows function, meaning the form, the structure of the molecule will determine its chemical properties, its physical properties, its function. Now, if you recall, ionic bonds typically occur between an atom with a weak attraction for electrons, so it has a low electronegativity. Typically they are metals, and another atom with a strong attraction for electrons, so it's high EN value, and those are typically going to be nonmetals. So looking at lithium, we see that it has an EN value of 1.0, while fluorine has an EN value of 4.0. So lithium has a very weak attraction for the electron, while fluorine has a very high attraction for the electron. As such, lithium will donate its electron to the fluorine, and in the process become a positive cation, while fluorine becomes a negative anion. You will now notice that both fluorine and lithium have a full outer valence shell, and they are now isoelectronic with the noble gas they're closest to. So lithium would be isoelectronic to helium because it has one shell that's full, while fluorine would be isoelectronic with neon because it has two shells that are full. You will notice that we place square brackets around both of them with an ionic charge in the top right hand corner to show that they are both ions. They are no longer the original neutral atoms, but charged ions that are stable. Please also note that I've written the ionic charges as 1 plus and 1 minus, not plus 1 or minus 1. By putting the charge at the front, that is referring to the oxidation number, which is something totally different than the ionic charge. We'll talk more about oxidation numbers when we get to the electrochemistry unit. Now that these ions are stable, they don't need each other anymore. So lithium has already given away its electron to fluorine. It doesn't need to be next to fluorine anymore. So why are they still bonded together? Because opposite charges attract. Due to their electrostatic attractions, the positive charge and the negative charge causes the lithium and the fluorine to attract one another. This is known as an ionic bond because it's a bond that's formed between two oppositely charged ions. Now, if you recall, ionic compounds tend to exist in a crystal lattice structure. So a crystal lattice structure is one where it just repeats over and over again, positive, negative, positive, negative, positive, negative. This imparts the following physical properties. A, they have a high melting point and a high boiling point. Let's look at this fluorine anion, for example. In order for you to remove this fluorine anion from this crystal lattice structure, you'd have to overcome all the electrostatic attraction from the lithium cations surrounding it in order to pull it out. And that's a large amount of energy required to do that. Hence the high melting point, high boiling points for these ionic crystals. As we have seen previously, water is a polar molecule with one end partially negatively charged and the other end partially positively charged. As such, the partial positive end of the hydrogen atom is able to latch on and attract onto the negative anion and pull it apart from the crystal lattice structure. Alright, so the partial positive hydrogens are attracted to the negative anion and they're able to pull it apart. Similarly, the partial negative oxygen end can latch onto the positive cation and pull it apart from the crystal lattice structure. This is why many ionic compounds are going to be water soluble, but only if the ion attraction, so the attraction that holds the ion together, is weaker than the ion dipole attraction, so the attraction for the water molecule. So if the attraction for the water molecule is stronger than the attraction between ions, then yes, it will be soluble. On the other hand, if the attraction for water is weaker than the attraction between ions, then at that point we would say it's insoluble. Finally, if you have individual ions that are freely moving around, either because they were dissolved in water, for instance, or melted into a liquid format, as long as these ions are free to move, you have electrical conductivity. A solution that conducts electricity is known as an electrolyte. Now, due to the nature of ionic bonds, we do not know which cation donated its electrons to which anion. So this lithium cation, we don't know if it donated its electrons to this fluorine, this fluorine, this fluorine, or this fluorine. We don't know, and in the end, it really doesn't matter. But because we don't know which pair of atoms were originally involved with the original exchange of electrons, we cannot refer to them as molecules. Instead, you're going to call them formula units, which is defined as the lowest ratio of atoms required to create a stable compound. So in the example of lithium and fluorine, you only need one lithium atom and one fluorine atom to exchange electrons in order to achieve stability. You don't need two lithiums or two fluorines, just a 1-to-1 ratio is necessary to achieve stability. Similarly, magnesium chloride only requires one magnesium for every two chlorines in order to donate their electrons in a way that allows them to achieve stability, while sodium chloride has a 1-to-1 lowest ratio and aluminum fluoride has a 1-to-3 lowest ratio. Finally, ionic compounds tend to be hard and brittle. This crystal lattice structure of alternating opposite charges, positive, negative, holds those ions tightly in place. So you're going to need a lot of force to get these guys to move. That's why the ionic crystals tend to be very hard. But if you do strike it with enough force, you can shift this crystal lattice structure. But in so doing, now you have like charges side by side. And as we know, like charges will repel each other, and that's why crystals generally don't dent. They're not usually malleable or flexible. Instead, when you hit them, they will shatter along these fracture lines. So, as you can see, form follows function. By transferring electrons from one atom to another, we form ions. These ions are then electrostatically attracted to each other, creating an ionic bond. And compounds formed from these ionic bonds have very unique physical properties. So with ionic bonds, electrons are transferred from one atom to another. But what if electrons are shared between atoms? This typically occurs between atoms with a strong or similar attraction for bonding pair electrons, so if they have a high electronegativity value. So typically this occurs between nonmetals and nonmetals as they have very high En values in comparison to metals. Since only one pair of electrons is involved in this bond, we call it a single bond. Over here we see two pairs of electrons, so we call it a double bond. And over here it's a triple bond because there are three pairs of electrons involved. Now these pair of electrons are referred to as bonding pair electrons because they're involved in the chemical bond. Since these ones are not involved with chemical bonds, they're by themselves, we call them lone pair electrons instead. Now in this type of chemical bond, neither atom gets to permanently keep the electrons. Instead, they're going to share them equally. And so half the time, the electrons will spend their time around this chlorine atom, orbiting it. Then they'll spend the other half the time orbiting this chlorine atom. And they'll just go back and forth, orbiting both atoms. Now, if I go to a casino and I win $1, but then I lose $1, am I richer or am I poorer? The answer is neither. I have broken even, which actually is a good thing. But similarly, when it comes to atoms, if you're losing electrons half the time, but then gaining electrons the other half the time, you're neither positive nor are you negative. Instead, you're going to be neutral overall because there's no net change in the number of electrons that is given to you or lost by you. And so molecules formed with nonpolar covalent bonds tend to have very strong intramolecular forces, so that's the one that's holding the molecule together, but very weak intermolecular forces, so that's what is attracting two separate molecules. So just keep in mind, when we say intramolecular, we are referring to the force that holds the actual molecule itself together. Right? So the intra, within the molecule itself. On the other hand, an intermolecular force is what holds two separate molecules together. Alright, so intra keeps the molecule itself held together. Inter holds two separate molecules together. Alright, so let's see how this form affects the function of molecules made up of nonpolar covalent bonds. First off, because these molecules are neutral and neutral, there's no positive, no negative because they're equally sharing electrons. Neutral and neutral, they don't really attract each other very well. And because they don't attract each other very well, it's quite easy to disrupt this intermolecular force. Alright, so during a physical change like boiling or dissolving, it is the intermolecular force that breaks up, that is being disrupted, alright, not the intra. My students typically have difficulties remembering this, so I ask them, is it easier for you to break up with a friend, or is it easier for you to break up with your arm? I would hope that it's easier to break up with a friend. Finding a new friend should be a lot easier than finding a new arm. Alright, so when we are undergoing a physical change, it's much easier to disrupt the intermolecular force than the intramolecular force. Okay? So, due to the weak intermolecular force, you're going to have a low melting point, low boiling point. Very little energy is required to overcome the weak intermolecular forces that hold separate molecules together. As we saw before, water molecules are polar. They have a partial positive end and a partial negative end. But positive and negative aren't super attracted towards neutral. And so typically, compounds made up with nonpolar covalent bonds are not going to be water soluble in general. Finally, since electrons are equally shared between the atoms, ions are not formed. Without these ions, nonpolar covalent compounds tend not to be electrically conductive. So thus far, we have seen completely opposite ends of the spectrum. What happens when electrons are completely transferred, resulting in positive and negative charges, and what happens when electrons are equally shared, resulting in neutral and neutral charges. But what happens when the electrons are unequally shared between atoms? So polar covalent bonds occur typically when two atoms have a strong but unequal attraction for bonding pair electrons. So looking at oxygen, we see that it has an En value of 3.5, while hydrogen has an En value of 2.1. This unequal sharing of electrons results in the formation of partial charges. So we use this lowercase d, Greek letters, for slight, or partial. So slightly positive or partially positive, and slightly negative or partially negative. In such bonds, electrons will orbit the atom with the greater attraction more often, providing it with a partial negative charge. So in this case, the oxygen, because it has a higher En value, will take the electrons, and electrons will spend most of its time around the oxygen and every now and then go back to the hydrogen. So the oxygen is not strong enough to completely transfer and rip the electrons off and keep it around itself, but at the same time it's not an equal share of electrons, so that's why we have a slightly negative charge for the oxygen and a slightly positive charge for the hydrogen. Due to these partial charges, we're going to have the following physical properties. In terms of melting point and boiling point, it won't be as high as an ionic compound because they have definitely positive, definitely negative charges that held them together tightly. And it won't be as low as covalent, nonpolar covalent compounds because they're neutral-neutral, so it's very easy to disrupt the intermolecular force. But the partial positive and partial negative will allow it to have something in the middle, a moderate melting point and boiling point. Again, since there are no ions formed, we will have no electrical conductivity in general, but they will be typically water soluble because the partial positive charge of one molecule will attract the partial negative charge of the other. In such instances, we would say that the polar molecules are miscible. They mix well together. Alright, so the last type of bond we'll be looking at is called the metallic bond. This typically occurs between metals and metals, hence the name metallic bonding. With nonmetals, it's pretty straightforward to see how they share electrons to achieve stability, to acquire that octet structure where there's 8 valence electrons in their outer shell. So for instance over here, they can share these 2 electrons, so half the time we have 8 electrons here, and the other half of the time we'll have 8 electrons over here. Same thing with the triple bond, sharing these 6 electrons, half the time the nitrogen on this side will get 8 electrons, the other half of the time the nitrogen on this side will get the other 8 electrons, and so we have a full valence shell from there. But metals tend to have shells that are less than half filled, so that means they have 3 or fewer electrons in their valence shell. As such, they have a difficult time combining to form a filled octet structure. So for instance, boron has a maximum of 3 electrons each, so even if you had a triple bond, you'd still only get 6 electrons. You could not fulfill that octet structure. So what can metals do? How can they bond in order to achieve stability? For this, we use the electron C model to describe how metallic atoms can form chemical bonds. Instead of sharing or transferring electrons between 2 atoms, they contribute their valence electrons to this electron C, a sea of delocalized electrons that occupy the spaces in between metal atoms. Now, when we say delocalized, what we mean is that the electrons are no longer stuck in one location. So for instance, if we look at this aluminum atom over here, let's say it releases its valence electrons. Those electrons that are released do not have to stay in the general vicinity of the atom where it originated from. Instead, these electrons are allowed to float away to a different part of the electron sea. This in turn acts as an electrostatic glue that holds these metal cations together. So this positive cation is attracted electrostatically to these electrons, and so are these other aluminum cations as well, and that's what holds them together like a glue. Although there are repulsive forces between electron and electrons, so negative and negative will repel each other, and cation, because positive and positive will repel each other, overall the net force of attraction is greater than the force of repulsion. So using this electron C model, we are able to explain many properties of metals. Take malleability for instance. Unlike ionic crystals, which shatter if you strike them with enough force, metals on the other hand tend to bend or dent. This is because the delocalized electrons shift along with the metal cations. So in this particular crystal lattice structure involving metals, if I hit them hard enough, the whole lattice structure shifts down, but you'll notice the electron C still acts as a glue holding it all together, and that's why metals are able to dent, while ionic crystals, when their lattice structure is shifted, and due to these like charges, they will repel and the crystal will shatter and fracture along these lines. Now, due to the strong electrostatic attraction between the metal cations and the electron C, metals tend to have higher melting points and high strength. In general, the more delocalized electrons an atom can provide or donate to the C, the tougher the metal is going to be. Now, unlike ionic compounds, metals can conduct electricity in their solid form. With ionic compounds, the ions had to be free moving, so they had to be dissociated into their aqueous or liquid form in order for those ions to freely move about the solution. But due to the delocalized nature of electron C, an applied potential difference will cause these valence electrons to move away from the negative terminal and towards the positive one. So the electrons are free to move around. This results in electrical conductivity. Finally, metals are able to form alloys. How is that possible? Well, the electron C allows for the attraction of any kind of metal cation. So we could have a copper cation and a zinc cation mixed with a nickel cation. It doesn't really matter what type of cation you have here, they are all going to be attracted electrostatically to this electron C. As such, a solid mixture of two or more different types of metals can be produced. Alloys in turn can have significantly different physical properties than the original metals. So for instance, brass is made up of copper and zinc. Copper is quite shiny and lustrous, but zinc is gray and dull. However, zinc is a lot more resistant to corrosion than copper is. By combining the two together and creating brass, brass now has the properties of both in the sense that it is both shiny and corrosion resistant. So to sum up, form follows function. How the electrons are transferred has a huge effect on their physical and chemical properties.